Southern Arizona has several stormwater infrastructure issues. Storm events are common during monsoon season. However, as climate change worsens, storms have become more and more prominent, and current infrastructure is not prepared to handle storms at this level. Miami is a town that has definitely experienced the negative effects of climate change, with intensifying storms and ultimately flooding.
Monsoon storms move through. Michael in Miami sending us this video. He saw trash cans floating down the road, cars and trucks stranded, even a person trying to walk across, something that is not safe to do.
The damage and costs associated with flooding have negatively impacted the local economy of Miami. And by further exploring the impacts of stormwater runoff in Miami, Arizona, we can surmise how to better explain and begin to solve some of the issues associated with stormwater infrastructure within the southwestern United States, especially the Sonoran Desert region. Miami, Arizona is a small mining town about 80 miles east of Phoenix. It experiences mostly arid conditions throughout the year, monthly precipitation averaging around 2 inches. This has been one of the rationales behind this town and other desert towns for further addressing stormwater infrastructure issues. Miami is surrounded by mountainous landscape and has one central wash adjacent to the base of a stretch of mountains. A recent wildfire in 2021 that has stripped the mountainside of its natural vegetation, in combination with the mountainous topography, has further intensified the volumes and flows of stormwater running through the central wash. This is why the basis of our design focuses on improving the central wash area and attempts to highlight the inability of Miami's current infrastructure in handling intense storms and possible natural disasters.
Our initial intentions with this project was to be environmentally friendly, impact the community positively, and maintain a low cost. However, once we found about the drastic issues Miami, Arizona has with its flooding, we saw that this solution would not be feasible, which is why we decided to model and size levees that would go along the wash in order to prevent drastic flooding of the town.
We began our process by using a web application called StreamStats, which was able to provide us with a basic watershed delineation and also gave us flow rate values for our different storm events, which range from 0 to 100 years. We then used AutoCAD and separated our watershed into 3 separate subbasins, which contributed to most of the water that was actually flooding through the town. We then began using a software called HEC-HMS. So into here, we had to input rainfall data, longest flow path lengths, soil types, vegetation cover, curve number, and lag paths. The vegetation cover we were able to estimate by looking at Google Earth, and with this vegetation cover data, we were able to calculate a curve number. Curve number is a function of soil type and land cover, and it basically just tells you that with a higher curve number, you're going to have more runoff. Lag time tells us how much time passes between peak rainfall and peak discharge. HEC-HMS was then able to generate peak flows for each one of our storm events. We then moved on to using a software called HEC-RAS, and into here we had to input our GIS data, our peak flows that we got from HEC-HMS, and then also our river geometry. HEC-RAS was then able to generate food numbers for each cross-section of our wash during each storm event, and we used this information to know where to put levees throughout the wash. And then we were able to simulate these levees also on RAS and put in various heights and toplets for different storm events depending on the intensity of the flooding.
HEC-HMS resulted in our peak flows, which are in cubic feet per second. HEC-RAS resulted in our food numbers, which range from 0.14 to 3.13. For each storm event. A fruit number that is less than 1 is considered subcritical flow or slow and steady flow. A fruit number that is above 1 is considered supercritical flow or rapid conditions.
This is our HEC-HMS model. We had to input 3 parameters into this software: our basin model, meteorological model, and control specifications. For our basin model, we input our watershed areas, the curve number for each basin, and also the curve number and lag times. For the loss method, we chose SCS curve number, and for the transform method, we chose SCS unit hydrograph. This is what allows the software to create a graph of runoff versus time for each watershed basin. Then for our meteorological data, we input historical rainfall data from NOAA Atlas 14 for up to 100-year storm events. We used the control specifications in order to run a simulation and selected the start and end date and a time interval to obtain peak flows for each storm. And then finally, we were able to gather our peak flow values for each storm for Junction 1, because that is where the combination of the flows is going from all three watersheds. And here are our peak flows.
This is our HEC-RAS model. First, we input the training data, which basically has our elevation data. Then we input the river geometry. The dark blue-red line is the center line of the river. Then we input our bank station, which is the dark red line. It just represents the edge of the channel from left to right. Then we inputted our flow path, which is the light blue line. It represents that the flow is going from left to right, upstream to downstream. Lastly, we inputted our cross sections, which are the light green lines. Then after we finished the river geometry, we were able to input the steady state flow data, and then profile 1 is the 1-year storm event, and profile 7 is the 100-year storm event. We obtained the flow values from HEC-HMS that are peak flows, and then we were able to run a simulation, which is over here. We have a steady state flow analysis. We were able to choose our flow regime. We decided to simulate subcritical flow, and then after we ran the simulation, we obtained our results. And as you can see on the left, these are all of the different simulations we ran. We were able to see the depth of flow that shows which areas are being flooded in Miami. We can also see our velocity profile, which is shown here. You can see with the gradient of color how the velocity of the flow changes throughout the channel. A dark blue color corresponds to low velocity, while the areas in red correspond to a higher velocity flow. Our results also included finding Froude numbers. This table over here on the left defines our profile in depth and gives us the values of where hydraulic jumps occur in the channel. These jumps occur when flow changes from supercritical to subcritical flow, and then we were also able to run a simulation that modeled levees within the channel. We were able to find the height of our levees for each storm event by looking at each storm event at each cross-section throughout the channel, and looking at the levee plan graphs and to find the ideal dimensions of each levee.
Our results indicate that the flow regime varied and hydraulic jumps occur. Hydraulic jumps occur when the flow goes from super to subcritical flow. Unfortunately, RAS is unable to model these conditions. Issues in our modeling could have resulted from not modeling culverts and homes. The height of the levees range from 5 to 20 feet tall, depending on our storm event. The higher the storm event, the higher the levee will need to be constructed in order to prevent flooding in Miami. Levees is the most realistic solution for Miami, Arizona. Due to the flow regime varying, therefore we cannot excavate the channel, and just the large amount of water that's coming into the town of Miami, we are unable to consider other alternatives like a detention pond.